All right, so maybe we can go immediately in medias res, if I can progress the slides. Well, before we go in medias res, let me actually really thank my research group here in Cambridge, who are great and who really contributed significantly to the things that I'm going to show you today. So this is really due to all of them, and also to all the funders that are supporting our research, from government and industrial stakeholders and also private trusts. So thanks a lot. All right, so let's start now. So this talk is really about the effect that machine learning, and in particular deep learning, had on the field of inverse problems, and in particular on inverse problems in imaging. And I'm going to focus on one aspect of where machine learning turned out to be extremely useful, which is to characterize or derive new ways to regularize an inverse problem. And so just a few bullet points here of the kind of things that I'm going to show you. So first of all, I really believe, and we have seen this in the last couple of years, that machine learning, and in particular deep learning, offers interesting opportunities for inverse problems. And this is true for two reasons. First of all, making something like the regularization, something like characterizing solutions to inverse problems via learning from the data, learning models for, let's say, images from the data, really turns out to be a very powerful tool for deriving high quality solutions of inverse problems. And you'll show, I'll make this a bit more precise what I mean with high quality as we go on. The other really very very nice feature of machine learning solutions such as neural networks is that, compared to the really very computationally hard problems that we usually use solving when we want to solve an inverse problems, like nonlinear PDEs and non-smooth optimization problems, once a neural network is trained, it's just an explicit application of linear and nonlinear operations. So this makes some things actually even computationally feasible for the first time. The other side of the coin, and this is where in particular, when we think about success stories of neural networks in all kinds of areas of computer vision, for instance, or image classification, many people in the computer vision community and so on have been somehow raising the fear that deep neural networks are going to solve all of our problems, and so are making everything else redundant. This is meaning that we just train a neural network to solve our problems. So this is definitely not true for inverse problems. They really, for inverse problems, because they are very hard mathematical problems, they're ill-posed problems, and we'll get to that in a moment. They can't be just solved with off-the-shelf neural networks. They need to be combined with mathematical and statistical modeling. And then what is extremely important for thinking about the application domains of inverse problems, where often we are solving inverse problems for decision-sensitive application areas. Actually, the mathematical guarantees, the mathematical scrutiny that that we are using to approach such problems, we still need to keep that in mind, and we need to use that also when thinking about how to combine inverse problem solutions with neural networks. So don't throw that out of the window. And one particular thing I'm going to discuss are that where we are trying to take this middle way between mathematical guarantees and performance through this data adaptivity, this capability of neural networks to learn models, are these learned variational models where we are learning a regularization and fit that into a variational reconstruction approach. And this is what I'm in particular going to present later on. So let's start with the kind of problems that we want to solve. So what is an inverse imaging problem? And so the bottom line of this is basically that we are measuring something that, you know, could be some tomographic machine, or you know, could be just your usual camera, let's say your photo camera. But we are measuring something that we are not directly happy with, that we are not directly interested in. We are interested in something that is hidden in the data. Let me call the data Y. That is related, a quantity, an image in most of the things that I'm going to show you, an image U we want to compute from the datum that is connected to the data via a process capital T that is a linear or non-linear so-called forward operator capital T. So a prototypical example for this kind of scenario in imaging is tomography, X-ray tomography, where what we want to compute, what a clinician, a radiologist wants to look at is an image, which you can think of is an intensity distribution of tissue density in the human body, for instance. Yeah, like in this case here is an abdominal CT scan or a slice through it. But what the CT machine is actually measuring are integrals through, we can simplify it like this, integrals through the image function. So integrals over the intensities that are measured at different angles and at different positions of the line. Yeah, so at different y-intercepts. And this is then the so-called sinogram that we are is being measured, that is parametrized by angle and by the positioning of the line. And every value that you see here, every gray value represents the value of the line integral. And this is also, if you would measure everything, this would be called the Radon transform of the image function U. This is a very old problem, goes back to an Austrian mathematician, by the way, Johann Radon, who asked the question, can you reconstruct a function from its line integrals? And in tomography, we are using this principle. The lines here in this case, the integral is basically the accumulation of X-ray energy that, or the accumulation of X-ray attenuation that, where the X-ray is attenuated by going through different tissues in the human body. And the problem in practical X-ray tomography is more difficult even than what Johann Radon was asking, because we are usually measuring, first of all, noisy versions of the actual X-ray attenuation, And we are also, when you think about so-called sparse tomography, we are not measuring as many line integrals as we have pixels in the image. Okay, there is this trade-off between how much are we radiating the object we want to look inside, and how much maybe we are also constrained by some physical nature of the problem, that we can only collect a certain from a certain number of angles, and the trade-off with the resolution we would like to have in the image. And of course, we want to have a very high resolution because we want to see a lot. Okay, so the problem, this is just an exemplar problem, inverse problem of that kind in imaging. In general, we can think of an inverse problem that we are measuring such corrupted data Y, and we want to compute a physical quantity from this measurement that is an image in inverse imaging problems. Okay. More broadly, actually, these kind of problems appear in lots of places in imaging, and maybe some of which are even surprising, like in computer vision, where we want to segment, classify different objects and images, maybe track them, for instance. So this is an inverse problem where the data Y would be, in this case, a video, and the quantity U that I want to reconstruct would be a classification, let's say a binary, or a labeled map of this image. Another inverse problem that actually I have been in love with for a long time is the one of image inpainting, where you are given an image, but part of this image is either missing because it's damaged, or you have an occlusion, for instance, in an image that you want to remove, and you want to replace with something that is suggested by the remaining part of the image. So it's basically, you can think of an interpolation problem. And again, this is you can formulate this as an inverse problem. Yeah. And then, of course, tomography appears in all kinds of forms. This is what you see here is positron emission tomography, where instead of X-rays, you have photons that are shooting from the body, from inside the body through a radioactive tracer that is injected. And then you can even think of inverse problems in the form of having a data set of images. So not solving an inverse problem on one image, but you have a data set of images and you want to, for instance, sort this data set into different classes. So it's a classification problem in a kind of abstract high-dimensional space where, I mean, this is here an example of graph-based clustering and then classification. So assignment of these clusters to particular labels. In this case, these are pathologies of X-rays, abdominal X-rays. And so again, you can think of this as an inverse problem where the quantity you're interested in computing is the label of a particular image. So you've given an image, you want to know what the label is. And the beauty of inverse problems in imaging is that they are extremely diverse, as you can see here. They have many application areas, and you can really, as a mathematician, I'm also advertising the area a little bit, as a mathematician, you can work on various aspects of these inverse problems along the way. You can work on the theory. Some of these inverse problems are really theoretically very challenging, and I'll say a little bit more about that later. You can work on computational solutions, you can work on even physics-based modeling, or you go really all the way to applications and do some interdisciplinary research. So this is really nice. Now, I hinted towards this already. So inverse problems are challenging, usually most of inverse problems in practice, because they are ill-posed. And so the kind of inverse problems that I've been working on and that I will show you also in this talk are linear inverse problems, where mostly the ill-posedness comes from well, properties of the forward operator, for instance, the forward operator being compact, and so you have, so that could be one problem. The other, and that combined with the fact that what I hinted at before, that in practice, in tomography, for instance, we are measuring usually much less than the number of unknowns in the image U that we want to compute, is what makes this problem underdetermined and so not uniquely solvable. And then the properties of the forward operator then also kick in by having noise in the measurements. And so if you have, you know, if your inverse is not a continuous operator, is not a continuous operation, then you get all kinds of stability issues with noise that you have in the data showing up also in your reconstruction and making it unusable. And so a typical kind of symptom of this ill-posedness is that one and the same measurement can be explained by two very different looking images. And so this is really where you are losing the continuity, and this is where regularization comes in to choose the right one of these two explanations for the same data, or almost the same data. Yeah? And so this brings me to regularization, which can come in various forms in inverse problems, but I'm going to focus on the variational regularization approach, where we are phrasing the computation of an approximate solution U to the inverse problem I've started out with as a minimization problem. So my U is a minimizer of an energy functional, which consists usually of two terms. One of them is the so-called data fidelity or discrepancy term, keeping the solution U true to the forward model, or let's say so my reconstruction U true to the forward model, and how much and this term quantifies how much the forward model should coincide with the measurements Y that I've measured. And a typical way to quantify, a typical metric to quantify is the L2 norm squared as a fidelity term. So least squares fit between measurements and the forward model. And then this alone would still have all these problems with continuity and non-uniqueness and so on. So what we are then doing is we are adding a regularization term that is now the one that picks the good solution, that narrows down the solution space of the inverse problem, and picks the one that you think is most likely. Yeah? With the prior information you have about the inverse problem you want to solve. And you can also see now here the link of this variational regularization approach with the Bayesian inverse problems philosophy, where if you're writing down a posterior distribution, I'm just briefly mentioning this to make a link to statistics. We're not going to use this later. But if you're writing down a posterior distribution for your for your reconstruction given the data, and you are computing as an estimator for this posterior distribution, from this posterior distribution, an estimator for your U, which is the maximum a posteriori estimator, then the prior that you have in your posterior basically turns into the regularization, and your likelihood turns into the data discrepancy term. Okay, that was a quick rundown of what the connection is to Bayesian inverse problem. So this really you can think of as the prior information, and a typical type of prior information that has been used a lot in inverse problems and imaging is the one of sparsity, where you're saying, well, I know that my image actually boils down to just a few significant characteristic features, and I can characterize those features. Yeah, and I would say one of the most widely spread sparsity assumptions on representing images is the one that I'm saying my image actually basically just boils down to the edges in this image. This is the most important information in this image, are the edges. And which basically you can again turn into saying, I can approximate the true image very well by edges and something kind of constant, so constant in between, so something that is piecewise constant, which boils down to saying that the gradient of the reconstruction is sparse. And that can in turn be represented by an L1 penalty on the gradient. Okay, so this is kind of sparsity promoting regularization and compressed sensing. Very quick rundown of that. In infinite dimensions, this L1 penalty on the gradient of U is actually better characterized by the total variation of the distributional derivative of U, which then puts this minimization problem into a minimization problem over the space of bounded variation functions. Okay, so this is also, and I'm actually I shouldn't say so much now because I'm going back to that, but that is something that has been extremely popular, and in inverse problems and image processing and so on has been really popularized by this paper by Rudan-Osher and Fatemi in 1992. Okay, and maybe one more thing to say before I go to the next slide is that there is also this positive parameter alpha here, which balances the need for regularization against how much your reconstruction should stick to the measurements y. And this choice of this regularization parameter alpha depends mostly on the noise level that you have in your data. Okay, so let's have a look at what this regularization is doing. Okay, I said before that this regularization really chooses the right reconstruction that explains the data. And so this is now a super simple inverse problem in the sense that the operator T is just the identity as a denoising example. So my data Y is my original image U plus white Gaussian noise. Okay, so every pixel has been corrupted by normally distributed noise. And so this is my Y, and then I compute now two solutions of this variational problem for two different choices of this regularization. One is the total variation that I've been talking a lot about just now, where you can clearly see this piecewise constant character. And the other one is the H1 semi-norm, just so you see the differences. And the total variation has been really has had so much success in inverse problems really related to images where you want to quantify something really because the edges are reconstructed very accurately, which is smoothed out if you're using something like an H1 semi-norm. Okay, so regularization matters. And also, this was now denoising. Let's just go back to my X-ray example that I had from before. This is again sparse X-ray tomography. So it's simulated, which means I have the ground truth. So you can think of the ground truth as a perfect measurements with full angles and very, very, very low noise, which usually means a lot of radiation. And now I simulated bad measurements, so sparse angle, I added noise. Then I do a very simple reconstruction first, just to show you how bad the reconstructed image can be, which is so-called filtered back projection. So this is the pseudo-inverse to the subsampled radon transform. And you can think of this as the kind of unregularized example. And this one is now the solution of the variational problem from before, where we've regularized with a total variation. And all the numbers, because they're showing up also later, when you see here numbers underneath the reconstructions, these are quality measures for how good the reconstructions are matching the ground truth. Okay, so this is the first one is the peak signal to noise ratio, and the larger this one is, the better is the reconstruction, the closer it is to the ground truth. And the other one that you see is, again, the larger it is, the better, and this is the structural similarity index measure. Okay, it's not so important to know exactly what they are, but they give you a good indication of some kind of indication, some quantification of how good the reconstruction is. So if you look at this and you compare it with the ground truth, I mean, fair enough, we had bad measurements, right? So it's you know, we can't expect to get exactly something that looks exactly like the ground truth. But you might also appreciate, also when looking here at actually the unregularized reconstruction, that maybe if we would have chosen a better fitted regularization, we might have gotten out a bit more details, right? Because even in the noisy image, you see a few of these, or I mean, now you know, of course, the ground truth, but so some things maybe we also imagine, but you could maybe imagine that you see a little bit more. Than total variation is really blocking, you know, is really doing this kind of blocky, very rough reconstruction. And the reason is just that we have somehow limited modeling capacity, limited by our ability to formalize things, maybe, but also by our ability to then solve the model, the variational model that comes out of what we are thinking could be a good fit to the kind of structures we see in this image. And this is really where I think something that is data-driven makes sense, because it helps us to go beyond what we can formalize. This is just another, you know, thought experiment, let's say, where really if we go back to this denoising example, I think, and you look at the TV denoised image, I think you could, if you just look at the noisy image, you could in your head denoise it probably better. And you can do this because you have seen grass, how grass should look like, or how sky should look like a lot of times in your life. Okay, and this is hinting towards maybe doing something that is data-driven. Okay, so the key idea here is to use, and here I really have neural networks in mind, because they are capable of really very accurately representing how sky should look like and how grass should look like and so on. So using very highly overparameterized models to complement our mathematical physics-based or geometry-based modeling, okay, of what images should look like, or how the data is connected to the images. Okay, and this works. This is just a teaser slide, so this really works. It works really much better to a certain extent. Yeah, And again, better, we can discuss later what better means. But so here you see, again, in the first row, you see what I've just shown you before. So the reconstructions without any learning, so just the TV reconstruction here in this case. And in the bottom row, without telling you exactly what this is, these are 3 different reconstructions with 3 different deep learning based approaches to solving this X-ray CT problem. And in all 3 cases, it's not just deep learning alone that solves the problem, but it's combined with mathematical modeling. Okay, and you can see that, you know, you can actually do a better job there. All right, so let's explain now how this works. Okay, and this slide is basically a disclaimer that there is a lot that is happening at the moment in the context of data-driven approaches to inverse problems, in particular deep learning-based approaches to inverse problems, which I've categorized here in these 4 different categories. And I'm only going to talk about one category, and I'm only going to show you what we have done in this category. And there is a lot more that is happening, but because of time, I can't talk about all of this. But just very, very briefly, just to explain the categories. So fully learned models is actually not what I told you we should do at the beginning, which is combine deep learning with mathematical modeling. But fully learned models is throwing away all the information, or at least throwing away the formalization of all of, you know, everything you know about the image you want to reconstruct and the physics that have generated the measurements, and express everything through a neural network. So you learn everything. The only place where mathematical modeling, where I wanted to say it's not totally forgotten, is the architecture of the network. Okay, but otherwise this is fully learned. And the disadvantage here are clear. You learn more than you should, than you need to, and this is also actually, you lose to a certain extent the computational feasibility, because you can't train these models for practically feasible data sizes that you have in real inverse problems. The other one is learned post-processing, where you get rid of one property of, in particular, this tomographic imaging or indirect imaging, where your data lives in a very different space to where your reconstruction lives. And in particular, if you think about the radon transform, or if you think about the Fourier transform also, that appears a lot in this inverse imaging problems, these are global transformations. So if you, and this is also where these fully learned models are super expensive. So you need to, in your network, you need to represent a global transformation, which means you need full matrix multiplications, basically. And there you lose the computational feasibility of training this. The number of parameters explodes, you run out of memory, and this is just not practical. In contrast to if you do learn post-processing, which means you first do a very simple reconstruction, a very cheap, simple reconstruction, like filtered back projection, for instance. So applying, if you can, the pseudo-inverse operator. Then you are in image space, and then you can have neural networks that are parameterized by convolutions, and these are much smaller. Okay, so okay, and the third one, so maybe one more point about this. So this is kind of nice because you are getting rid of the inverse problem by just solving it in a dirty way, but is also not the most elegant way, maybe, because you are first doing a very bad reconstruction, and then you're cleaning up the mess in some ways. So I think has some disadvantages and disadvantages, but I would say the third one is maybe something that I also quite like in a way. So this is intertwining the two things, the inversion and the learning, in terms of learned iterative schemes. And here you can think of, very roughly speaking, you have a variational model, you write down explicit gradient descent for minimizing your functional, and then you put in neural networks in the gradient descent steps. So you don't just take the gradient of your starting energy, but you then add degrees of freedom there to the regularization, for instance, and so on. And then you learn this highly overparametrized gradient descent scheme, where you then not take a lot of iterations, but let's say you take 10 or whatever these learned iterative schemes are taking. They're also called learned unrolling, because they unroll a variational reconstruction framework. Okay, so what I'm going to talk about is learning the regularizer, and so let me just go there and just say why I've been really mostly fascinated, or mostly looking at this data-driven approaches through learning a regularizer framework, and the reasons for that are twofold. I mean, I have been working with variational regularization models for more than 10 years. And I think they are very powerful for various reasons. One is that we really one is that we have a mathematical analytical handle on them. We know what to tweak and how to set them up, so we get a well-posed model in the end. We have also, because I think learning the regularization makes most sense for most of the things we're looking at, the regularization and the data model are really decoupled. And also, you know, how the data, so both the data model in terms of the forward operator, but also the data model in terms of the statistics that you have in the noise that will determine your data, the metric you're using for your data discrepancy term. So I think it makes sense to use this decoupled thing and slot in the neural network for the regularization, and then still solve a variational model in the end. And this is what I'm going to show you now. Okay, so the idea is we look at a variational regularization model. Maybe I should say, is there any question maybe at this point? Because I've minimized all of you to so that I see my slides. But does anyone want to ask something?
So it seems that you have no questions, so I think you can proceed. Okay,
good. I mean, the actual stuff I'm actually getting to now after a very long introduction. Sorry about that, I sometimes get lost in this. Okay, so variational model, and now I want to learn the regularizer, and I'm only going to focus on linear inverse problems. This is really what my bread and butter is. Nonlinear inverse problems, there are some works which are looking at data-driven approaches to nonlinear inverse problems, but they are so infinitely harder, and yeah, and it's really a very different story if you go to nonlinear. So let's focus on linear and on the variational setup, and I want to learn a regularizer. Okay, and the idea that we had is really to learn a regularizer with a neural network, parameterizing the regularizer as a neural network. But before you attempt to do something like this, right, you first look at what has happened in the literature in the past, how people have actually made regularizers data-driven. And of course, you know, this story started much before neural networks. Yeah? And so maybe let me just comment on a few machine learning type approaches to regularization. One of them is dictionary learning, okay, in the context of sparse coding, of sparsity promoting regularization, where the idea is you represent your reconstruction as a linear combination of some basis functions or dictionary elements. Doesn't need to be a basis, yeah. And then you so you say, this is my representation of the solution, and in addition I know that this is a sparse representation in the sense that most of the coefficients gamma I here are going to be 0, and this is here given by the regularization term. Okay, so this is an L1 penalty on the vector of coefficients gamma I. And so this would be just sparse coding if the phi i's are given, but if you do dictionary learning, you're also optimizing over the phi's after, again, parameterizing them in some way, okay? So this has been around a lot. Interestingly, it hasn't made such a huge impact in the inverse problems community with this kind of, indirect imaging stuff. It had a lot, there was a lot of works along these lines in the signal processing community, where we don't have this this forward operator basically. But I mean, there are some works that have still done this. Another one is the idea of how can you enter learning-based approaches in regularization is via this plug-and-play approaches or black box denoisers, or the new kind of version of this is regularization by denoising, where you say a lot has happened for image denoising, of coming up with good smoothing procedures for noisy images, for turning a noisy image into a clean image. And so wouldn't it be great to take advantage of that and turn a kind of off-the-shelf denoiser into a regularization for an inverse problem, for any kind of inverse problem we want to solve. And this is what this regularization by denoising is doing, for instance. In a particular way, you can take a denoiser that needs to fulfill certain properties and turn this into a provable regularization. Yeah, and so provable regularization, what I mean by that, by the way, is that usually what you want is that if you let the regularization parameter alpha here go to 0 and your noise level go to 0, that you are converging to so-called R minimizing solution to this problem, or kind of ground truth solution that fits where TU fits Y perfectly. Okay, and so this works, and you can imagine a lot has happened also with deep learning and denoising. So you can just take a learned image denoiser and plug it in here, and lots of people had successes with that. And also the reason is that for denoising, of course, your training data is super large in theory, because you know there are so many images. There are so many images on the internet. Just ImageNet, for instance, is a really huge database that you could just use. That it's much easier to create a training set for denoising than for an inverse problem. The third one is bi-level optimization, where you say you have your variational problem and you take your regularization and you parameterize it. Usually these are low-level parameterizations, so linear combinations, for instance, of different regularizers, where the lambdas are the weights in front of your different regularization terms, or an infimal convolution of different regularizers. And then you learn the lambdas, so the coefficients in these linear combination infimal convolutions. You learn them by saying that the solution that comes out of your variational approach should be optimal with respect to this choice of lambda, optimal for a particular evaluation criterion, where you have a way to evaluate how good the U lambda is. And the very typical approach here is that, again, you have a training data set of noisy and ground truth images, and you compare your U lambda with the ground truth image, and you choose the lambda which is best fits the ground truth image in some metric. So this, in principle, you could also do this, by the way, with neural networks. One disadvantage of doing it in this bi-level setting is that it's computationally, these bi-level problems are very, very tough. I mean, we have worked on that ourselves, and I mean, I'm still, you know, fascinated by bi-level optimization. But the problem is that for really computing optimal parameters lambda here, you need to solve your variational problem. So you iteratively minimize this, right? And for each outer iteration of minimizing this, you very accurately need to solve the minimization problem in your constraint, and this is just very costly. Okay, so let's go to deep neural networks for regularizers, and I want to show you one way of how you can do it, which is not bi-level, but it's decoupling the variational problem from learning the regularizer. And this is our learned adversarial regularizers, and this is joint work with several people. So Marcello Carioni, who is a postdoc in Cambridge, Søren Dittmer, who is a postdoc in Bremen and in Cambridge, Sebastian Lunz, who is a former PhD student of mine, now went to the city and started working for a hedge fund. Shubho Mukherjee is a postdoc also with me in Cambridge. Ozan Öktem is a colleague of mine from KTH in Stockholm. And Zach Shumyalov was a is a super talented undergraduate math student who joined us a couple of summers in these projects. Okay, so how do we now train the regularizer? So I said we are going to decouple it from the variational problem, but in order to understand how to train it, we still need the variational problem as an inspiration, right? As to understand what do we want the regularizer to do. So if you look at the variational problem, what we basically want is, so the regularizer acts as a penalty. It should penalize the kind of noise and artifacts that you know, we expect to see from inverting the forward operator capital T by, you know, just the least squares fit. It should penalize those, and it should be large for noisy reconstructions, let's say, and it should be small for the kind of reconstructions we want to see, for the kind of images we want it to favor as solutions to this inverse problem. And we have basically just thought of doing this by training the regularizer almost like a classifier between the two classes, okay? And I called them here good guys and bad guys. So what we did basically, or how you could do this is the following. So you have your inverse problem. You have a good representation. You have a good way to create images that feature the structures you want the regularizer to favor, to be small for. Yeah? So in CT, for instance, okay, in computer tomography, what you could do is you could take some very high dose CT measurements from phantoms, for instance, yeah, and you take those as your good guys, as the ones that represent the kind of reconstructions you want to see. And then you create another data set with the bad guys that show all the artifacts and noise that you see in reconstructions that are taken from the typical data that you want to solve your inverse problem 4, right? So let's say sparse CT, okay? And the bad guys you can create in different ways, but you could think of the bad guys being solutions to a baseline reconstruction approach that you want to improve upon, okay? So you want a method that is better than what the bad guys are looking. And here we, for a CT, for sparse angle CT, we used, again, the pseudo inverse, the filtered back projection to construct the bad guys. Okay, and then we do what I just said. So we train the regularizer in this adversarial manner. Okay, so this is why we call the regularizer the adversarial regularizer, to be small for samples from the distribution of the good guys that I call PU, and large for samples from the distribution of the bad guys that I call PN, where N stands for noise and U here stands kind of for the ground truth. Okay, so this is what I want to compute. Okay, so and how do we do this? Metric wise, so because we need to understand what we put, yeah, so how do we optimize? How do we, what is an evaluation criterion for such a regularizer? And we chose the 1 Wasserstein distance for this, which is almost what I said before, plus a 1 Lipschitz constraint on the regularizer that I'm getting, okay? So this is just what I said before. So what I'm looking for is a regularizer R that is large if I feed it with samples from PN, and that is large if I feed it with samples from PU. Okay, so this is what I'm saying here, and this boils down to the 1 Wasserstein distance. Now, the nice thing about this is that we learn the regularizer, we train the regularizer really to learn image statistics, in the sense that the good and the bad guys do not need to be paired. This is really a way of optimizing the regularizer in a distributional sense, right? We want on average that the regularizer makes this large and this small, which is nice because it's unsupervised. Unsupervised in the sense that the bad guys and the good guys don't need to correspond to each other, which is super nice in inverse problems. Neural networks are coming in by how I parameterize this R, right? Because I'm not going to optimize here over all 1 Lipschitz functions, but now I'm making some approximations and I'm narrowing this down somehow. And so one of them is that I parameterize my R here, my my set of possible solutions. I parameterize this through a convolutional neural network, okay? And I can even make this neural network, and this is kind of nice also when you think about the variational problem that comes out, I can even make this convex. There is something that is called input convex neural networks that has been proposed by these guys here, where the regularizer that comes out is actually convex. And then I can make the regularizer that I put into my variational problem strictly convex by just adding a little L squared term, L2 squared term, okay? And then practically, I'm training the psi theta. This is the neural network regularizer that I'm training, and I'm training it with this, okay? So here I've just put in now a neural network instead of all 1 Lipschitz functions, and I've taken the 1 Lipschitz constraint and I'm approximating it. Okay, so this is now my objective. And so this is basically the rundown of the algorithm of how I'm training this. So the first thing is I'm creating the 2 data sets, okay, the PU and PN. So then I train the regularizer in this by optimizing the network parameters theta for this loss function. And then once I've done that, I take the learned regularizer that could be convex or non-convex, depending on how I parameterized it, and I put it back into the variational problem. Okay, and then I use some numerical approach to solve this. Okay, so here we have been a bit lazy. We use just subgradient descent. And the nice thing about this is, of course, that if I do this like this, then I really can get well postness of the resulting variational problem, and I get this for free. Okay, so I'm not going to spend a lot of time here because this is really just off-the-shelf results. In the convex case, so the ACR is the convex one, the AR is the I let it free, so this could be non-convex. But in both cases, I get well postness. Of course, in the non-convex case, I lose uniqueness. And also the stability is the stability that I'm getting with respect to, you know, changes in the data. How much are they affecting changes in the reconstruction? I'm getting stronger ones when I look at the convex version. Okay, so this is nice. And we have actually also, so when you think about what we are doing here, that we are first training the regularizer and then put it into the variational problem and use it there. One thing that comes to mind that came to our mind, and that I also got asked before when I gave this talk, so that also came to mind to other people, is that you could iterate somehow this process, right? You could think of training this, then putting the regularizer back in here, compute solutions to the variational problem, and then put those solutions back into the set Pn of the bad guys, and then train the regularizer again, right? So you use your variational problem. If some of you know about generative adversarial network, you use your variational problem as a generator that challenges the discriminator, which is represented here with this loss function here, right? So you could think of it somehow like this. And this is
sorry, Carola, you have 5 minutes more.
Okay, thank you.
Okay.
Thank you.
Sorry for that.
No, it's good. Actually, I said I'm going to finish in 15 minutes, but sorry. Yeah, I'm actually almost done. So this is how we then actually what we did. We kind of alternated between training the regularizer and improving it through, in this case, not directly a solution to the variational problem, but a network that attempts to compute, that attempts to, on average, solve the variational problem over the training set. Okay, I don't know if this was so understandable, but I can explain more another time or later or whatever. Okay, so but here we are kind of updating the adversarial regularizer with and making it better. This is nice, and we get also maybe along the way a generator network that also solves the problem, which means eventually we can decide not to solve the variational model in the end, but use the generator network to solve it, because we trained it at the same time. Okay, results, and then I finish. So this is now for sparse angle CT. Okay, I'm not going to bore you with the details, but again, this is an undersampled problem corrupted with noise, and the reconstructions, and this is trained on an open CT data set by the Mayo Clinic. So abdominal CT scans. And I'm going to show you reconstructions with filtered back projection. So this is our baseline. This is the pseudo-inverse reconstruction, total variation, the adversarial regularizer that has this clever updating in it. Okay, the convex adversarial regularizer, and this is a kind of a state-of-the-art, data-driven, deep learning-based reconstruction approach that is belongs to the class of learned unrolling. Okay, learned iterative schemes. One can tell that I've spoken for too long because I'm losing my voice. Okay, so here you see on the left ground truth, again simulated. So this is our comparison. On the right, it's filtered back projection, or it's the reconstruction. Okay, so this is filtered back projection. Again, these numbers tell you how good it is, kind of. This is total variation reconstruction. Okay, so you can see the numbers definitely jumping up. And also you get, crisper results, you get rid of noise and so on. You really boil down your reconstruction to the kind of structures, to seeing the structures rather than the noise, okay? This is what you get with the convex version of the adversarial regularizer. And here, you can be, well, we were happy because we got, quantitatively better, definitely by 1 dB in the signal to noise ratio. But the convex regularizer at the moment is really constrained by the kind of parametrization we are using. So here, I think there is much more to gain, and we have some preliminary results that I don't want to spoil the story, because we still need to inspect that a bit more. But we have some preliminary results that definitely show that if you use better parametrization for the convex regularizer, you can also get better results here. But anyway, this is what we have at the moment. And this is the non-convex version, the one where with the clever updating rule. And here you can really see the gain. You can really see that this, I mean, in comparison with the total variation regularization, this is like a huge jump, again, similar as the jump we had from filtered back projection to here. And this is the baseline learned iterative scheme. One thing to really highlight is that the learned iterative scheme is still actually quantitatively better than what we are getting with the adversarial regularizer, but it doesn't have any guarantees. Okay, so all the well-posedness that I've shown you before is why we want to stick to the variational problem. Okay, so now I'm going to finish. There are lots of things that you can look at towards extensions. There are lots of open problems. One, I just said, what are good, better parametrizations, but still preserving convexity. Convexity is so nice for so many reasons. But there are, many more things that you could do. How could you impose more qualitative properties in the regularizer? We recently looked at that together with Martin Burger and Schubo to impose a source condition on the regularizer, for instance, things like this. So you can do a lot. You can think of a lot of extensions, and then of course the generalizability of all of this regularizer and so on is also. There are lots of open problems here. Here we only have empirical investigations and Sebastian Lunz's thesis to look at this. So there's a lot that you can still do. So takeaway messages. The role of deep learning, I think, in inverse problems is really the one of something that can capture prior information about the problem you want to solve. I focused on the regularizer mainly, and I really think this is the thing we can get most out of it. But you could also think about the forward model, that you might have a very imperfect forward model because the exact model is maybe too expensive, and you could use a neural network also as a proxy for that, right? To correct the forward model. And indeed, we actually did something with Simon on that recently. I think the beauty of these variational approaches or of fitting in general data-driven approaches into our rigorous mathematical frameworks is that we get guarantees. And I really think that this is the most promising way forward in inverse imaging problems. And as I said, there are many open questions. So I thank you very much for your attention. And I'm sorry that I took so much longer than I actually said I would. Thank you.